As we're thinking about laws, we want to concentrate and have on the ones that are unquestionably laws. Unlike those things that can't be observed or repeated, that are claimed to be laws and aren't. And the point we've tried to make is you see it everywhere. Certainly in the world around us, we have this from our own experience, and we see it even in the fossil record, or certainly we see a downhill process. I think we see it very obviously in the earth itself. As we look around us rather dramatically, we see erosion taking place. Is this going uphill or downhill? It's much more downhill than we realize. In fact, we spend a good bit of time measuring how much sediment is being transported by the rivers to the oceans. And you can put the little measuring devices in the mouths of the rivers and multiply times the flow, and you get an idea of how much sediment is being delivered. 27.5 billion tons is being delivered to the ocean by the rivers every year. Now that number doesn't mean a whole lot, but let's put it this way. That's enough to fill a freight train that would reach all the way to the moon and halfway back. Every year, dumped in the ocean. Now that's not an uphill process, is it? It's dumping the continents in the ocean. Now, there's a lot of mass in the continents, and you can do some pretty quick, simple calculations to see how long this could go on, and we wouldn't have continents, and it's not very long. The Earth's been here supposedly 4.5 billion years, and you couldn't do it at this rate more than about 14 million. But, of course, we've still got big continents. But it couldn't have been going on anything like the age of the Earth. Well, of course, if you move it over here, we're told about the principle of isosity, and you push down here, and it pumps up over here. But you can do those calculations and check those simple explanations, and they don't work. Sometimes they try to explain it in terms of seafloor spreading, and it accounts for about 1/8 of the total problem. It's going downhill. It's just like everything else. When we look in the heavens, I think we see one of the most dramatic examples of this process. While the evolutionist says everything in the world is going uphill, everything in the world and the universe around us is doing just the opposite. You see astronomers that talk about stellar evolution and galactic evolution, and everything they talk about is going uphill when the fact is it's opposite. You go out on an average night, a good observer can observe about 100 of these little shooting stars, we call them. Little bits of matter that are burning themselves up as they crash into the atmosphere. Here is probably something that's come apart in the universe and now is coming into the atmosphere and burning itself up. This is dramatically downhill. Some of them are very dramatic, as we see them in meteor showers. This is a Linoid meteor shower. This is one that approached the sun several years ago and came back around this way, coming apart and then crashing often into a heavenly body. Here, like the moon, on our side, on the backside, unprotected from the earth, its atmosphere, it's just been beat to a pulp. Again, this is not an uphill process. Something's come apart, something's crashed in, it no longer is in existence, and we see this on Mercury, and we see it on Mars. We see huge craters, and this is evidence of downhill everywhere we look. We look up into the sky and we see the beautiful comets, and here's one, the Hale-Bopp comet, that is coming apart, which is what we see comets do. This is the Ikeya-Sika comet from a number of years ago, similar to the Saho 6, one of the sun grazers. Notice NASA's description: a family of comets created by successive breakups from a single large parent comet which passed very near the sun in the 12th century. This comet, known as Saho 6, did not survive. Doesn't sound uphill to me. Fred Whipple of the Smithsonian Astrophysical Observatory, one of the leading experts on comets in the world, in his book, Mystery of Comets, says comets tend to split in pieces, particularly when they're near the sun or Jupiter, but also when they're quite undisturbed in space. Some comets seem to tire out and die. Isn't that a surprise? Here's a picture of one that tired out, died, split into many pieces. This is the Shoemaker-Levy comet of 94. NASA provided us a dramatization of what happened. It crashed into Jupiter, each piece with the force of many megatons of an atomic bomb, just boom, with huge force, crashing in. Again, the thing that came apart went downhill and then crashed into the surface. Here on Jupiter's moon Ganymede, we can see this string of craters which indicate something came apart and then boom, 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 the parts crashed one after the other, 13 fragments. We see this on the moon. Here is the streak here that indicates this string. Why are the craters lined up? Because something has come apart and then the parts crashed. And it fits the picture that we see everywhere we look in the heavens. The thing that we see most obviously when we look at the sky is the sun. We're told that it's dissipating 4.5 million tons per minute in thermonuclear reactions. We do know it's, quote, figuratively, burning up, dissipating energy out through space, not only through the normal stellar processes, but through the prominences and flares that you see blasting out on the side. Here's a huge one, blasted out compared in mass to the Earth. Huge. 4.5 million tons per minute, and then boom, other things like this. In addition to that, the solar wind dissipates another million tons per minute. And so we've got at least 5.5 million tons per minute. That's not helping it a whole lot. Now, there's a lot of mass there, and it's not going to go out tomorrow. But it's a downhill process, and pretty dramatically downhill. Now then, multiply that times what you see when you look out in the sky. Most of what you're seeing out there is stars, billions and billions of stars that are dissipating millions of tons per minute. What's going on in the universe? It's dramatically going downhill. And that's with just the normal stellar processes. When we look at things like the planetary nebula, beautiful fireworks in the sky. Here's a star that just blew up, 10 to 30% of its mass, blasted into an outer shell from a dying sun-like star producing the planetary nebula known as the helix. Here's another beautiful planetary nebula, boom, like God's fireworks. But it's not an uphill process when something blows up and leaves this spray of sparks. Is that uphill or downhill? Some of them are just spectacular and even symmetrical as they blast themselves out of existence. This dying star throws off shells of glowing gas. Here the radiation floods out in the surrounding gas, causing it to fluoresce. And when we see these glowing gases, sometimes we're told, well, look, it's heating up and condensing. Now, what's happening? It's blasted out, and the shock of the blast excites the particles like we see in the fluorescent lights here and causes them to fluoresce. It's an indication of an explosion. And here NASA says this radiation floods out into the surrounding gas, causing it to fluoresce. Over the next several thousand years, the nebula will gradually disperse into space and the star will cool and fade away. That's what we see. But the planetary nebula are just kind of pitiful compared to the novas and the supernovas, which not just blasting 30% of the mass, but completely blast themselves out of existence. This is one of the last ones that we saw, 1987. And we see in the inset the way the star looked one night, and then beside it the way it looked the next night. Tens of thousands of times brighter overnight. Now the normal star is like the sun, 5 million tons per minute. And then 10,000 times more than that as it blasts itself out of existence. We see the remnants of some of those explosions. Here are one of them in the Crab Nebula. As NASA said, this is the mess that's left when a star explodes. It's beautiful. This one happened to be observed. A number of cultures observed and recorded this explosion that took place in 1054. And we know of the Chinese and the Arabs, the Native Americans, possibly two others, but these recorded it and saw it. So we know what's going on here. Now we got glowing gases. Maybe it's coming together? No. It's blowing up. Number of these supernova remnants are seen. This is a spectacular one, blinding flash, which the concentrated power equals that of 10 quadrillion suns. I mean, the sun is degenerative. 10 quadrillion suns. How do you get an uphill process when everything you see is just not only degenerative, but dramatically degenerative? Here's the description of NASA. This is N49's cosmic blast. Scattered debris from a cosmic supernova, an explosion, lights up the sky just like fireworks. We can get some predictions and maybe some ideas about how long this has been going on from the fact that these supernova remnants appear about once every 25 years in our galaxy. And we're not sure why, but it's pretty regular. And over the past 100 years, we've seen this happen. Actually, further back than that, of course, 1054 gives us a pretty good range of observation. This is the conclusion, and I don't know of anyone that argues with it. That's what is indicated. Well, if it's one per 25 years, we can see immediately how many we ought to be able to observe if it's this old or if it's that old. We can make some predictions, which is the way science tests models. If we're looking at 1,000,000 years, then we ought to be able to see 40,000 of these things at one every 25 years. Pretty simple. Well, no, because some of them are behind gas clouds and some of them are near novas that get dissipated when it blows up. So we grant every possible exception and even exaggerated a little bit. And they'll say, well, you still, maybe not 40,000. You ought to be able to see over 7,000. Okay. But what if we're looking at only 7,000 years? Well, that's a very different picture. We would predict one every 25 years, 280, maybe some of them we couldn't find behind gas clouds, something like 270. Very different predictions. 7,000, less than 300. Which one fits the facts best? What do we actually observe, which is what science is about? So far, we've been able to find 260. Isn't that interesting? But we see when we look at the news and we look at the propaganda that we're inundated with, articles like this. This is from USA Today. Hubble telescope captures the birth of a star. Boom, here came a star. Well, you read the article and say, well, it actually takes well over 100,000 years for this to happen. And, okay, well, nobody saw it last night, which is the impression you get when you look at the headline. And we're not seeing it happen. We're seeing things that they say infer that it's happening, or at least that's the impression they like to leave you. The experts will tell a different story. Here from Science Magazine, 1990, we have yet to directly observe the process of stellar formation. Nobody has seen that, in spite of these misleading headlines. But we're pointed here in Discover Magazine to the stellar nurseries. Like every night we can see new stars popping out, and of course we should. You calculate how many are out there, you ought to be able to see them forming because they're just a mind-boggling amount. We're pointed to the Orion Nebula. Spectacular. Glowing gases. Shocked from an explosion. But here's a nursery. Here's where they're just popping into existence, or should be. We hadn't observed it, but this is where it's happening. Just trust us. Here's what NASA calls a star factory. Why? Well, we've got glowing gases. Oh, well, here we've got glowing gases. Yeah, but now we saw this explode in 1054. We know what this is. And so when we see this, that can't be. We got to explain it somehow. And all we can see is glowing gases. And when we know how the glowing gases got there, we know it's not star formation. It's blowing up of a star. J.C. Brandett addresses the problem in his book, Sun and Stars. He says, contemporary opinion on star formation holds that objects called protostars are formed as condensations from stellar gases. Okay, you turn loose gas from an aerosol can in this room, and the gas just comes together in a little ball up here, doesn't it? Or does it? What happens? It doesn't condense, it spreads out. I mean, we know that. You see the smoke from the campfire come up, and it doesn't gather together in a little ball. It spreads out and dissipates. But here they're imagining that it condenses. Well, the second law says things are going to get more disordered. It's not going to get more ordered. He goes on to say this condensation process is very difficult theoretically. In other words, we can't make it work on paper. No essential theoretical understanding can be claimed. In fact, some theoretical evidence argues strongly against the possibility of star formation, and of course it's not theoretical, it's the second law of thermodynamics that says that ain't going to happen. Oh, but you've got gravity that attracts, yes, and that you start compressing gases, and what happens? It heats up and it pushes back, doesn't it? You've got expansive forces as well as the attractive forces, and you can measure both of them. The expansive forces are 60 times greater. And so it's going to come together. Not when the expansive forces are 60 times greater. Yeah, well, I know gravity works and there's an attraction, but measure the two and see which one's going to win. Very powerful evidence argues against this. And while it'll tell you in your earth science textbooks, we know exactly how this happens, the authorities know better. Here, Abraham Loeb for the Harvard Center of Astrophysics. The truth is we don't understand star formation at a fundamental level. Now, if you're an earth science teacher in high school, you can tell folks we know. But if you're head of the Harvard Center for Astrophysics, you have to admit, no, we don't have a clue. And I think we know which one is more dependable. Here's another reference from Science 2002. Stars are among the most fundamental building blocks in the universe, and yet the processes by which they're formed are not understood. So don't let the teachers fool you. They don't have. How do you get gas which spreads out to come together? And they don't know. Godfrey Burnbridge, a more frank, very leading authority in our nation on astronomy, says, he's director of the Kitt Peak National Observatory, if stars did not exist, it'd be very easy to prove this is what we expect. But they're burning up. They're burning up in quotes. They're dissipating energy. It's all going downhill. And it's been going on billions of years. There ought not to be any. How do you get them together? Well, you can't in terms of what we know today. All of the authorities that I'm quoting are atheists. They're naturalists. I want to make an exception and refer you to the statement by Dr. George Mulfinger, who has his PhD, recently deceased, but had a PhD in astronomy from Syracuse, but was a creationist. Now, I want to make that distinction. And, of course, he referred to the fact that one of the problems is that it's unscriptural. Genesis 2:1 says all the hosts were finished. All the stars and the host of them were finished when God created. So he says, really, there are only three problems, he says, regarding star formation. The first is it's unscriptural. And the second is it's never been observed. And the third is it's theoretically impossible. But aside from those three problems, he says it's a real winner. Which I think is a pretty good analysis. But even those who are atheists say very similar things. We've been talking about stars. Let's multiply the problems in forming stars by hundreds of billions of times, and we see the problem we have explaining galaxies, which not only have the problem of forming the stars in them, but forming the organization, the collectivity of stars. How did they get together when the second law says everything goes the other way? Martin Rees, astrophysicist, writing in the Dallas Morning News a few years ago, says the most basic questions about galaxies are still not understood. If galaxies didn't exist, we'd have no problem explaining that fact. That sound familiar? Kind of like a refrain. It's not supposed to be coming together, not naturally. And we see beautiful formations up here, these pinwheel spirals like M51. This forms when the center part turns faster than the outer part, like the ice skater pulls in their arms and spins faster and slows down when the arms of these galaxies act like that. The spiral-shaped wave patterns from the galaxy's center whirl around the core 3 times as often as those 6,000 light years out, says the team. All but guarantees the galaxy's bright inner pinwheel is destined to wind itself up. Now, it doesn't take many turns to just completely wind itself up into this amorphous disk, not like the spiral arm disk. Well, how fast is it winding itself up? Well, it's pretty fast, just a few 100,000 years, not the 20 billion or 15 or 13 billion that they proposed for the age of the universe. It looks like it hadn't turned more than once or twice. Just a few 100,000 years is the most you can get for this. And what really gets difficult is when you look at what's called the barred spiral. And here's this straight bar right across the middle, and it hasn't twisted at all. Just half a turn, and that'd be messed up. And that would take just thousands of years, and there it is. And why in the world do we have bars in the middle of these spirals like this? I think it may be that the Lord's just looking down and saying, nah, 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 nah. You can't explain this. Because just in a short period of time, it would be destroyed. It wouldn't be like that. When we have seen more through the Hubble telescope, it's been anticipated. Now we're going to explain natural origins, but the further we look, the more difficult it's gotten. Here reported in the Dallas Morning News, astronomers, the Space Telescope Science Institute released the deepest ever view of the universe Tuesday. Long duration exposure reached out to a point just a few million years from the Big Bang. Look way out to just right. We can almost see the beginning out there. And what do we see? A wide range of galaxies. We don't see baby galaxies. We don't see forming galaxies. We see completely mature sizes, shapes, and colors, everything that you see everywhere else. Looking back to the beginning, you should see it gradually forming, not at all what we see. This was reported by Gemini Observatory, showing how this should have developed theoretically from the little baby galaxies, the little seeds, finally to the more mature galaxies that we see with the spiral arms, and pointed out that, well, here's the headlines. The faintest spectra ever raised glaring questions. Why do galaxies in the universe appear so mature? It's massive and mature right back to what they call the beginning. Richard Cowan, University of California at Davis, comments on this. He says galaxy formation theory is in peril. Over the past 18 months, several teams have found so many massive galaxies from this early epoch that the theory is being stretched to the breaking point, several astronomers say. In other words, we can't explain this. It just flies in the face of what we predict. Notice the comments of James Trefil, who's professor of physics at George Mason University, one of the more famous astronomers in the country. He says, it seems the more we learn about the basic laws of nature, and he's not talking here about Sunday school literature. It's the basic laws of nature, what we're talking about tonight. The more those laws seem to tell us the visible matter, the stuff we see, shouldn't be arranged the way it is. That is, if it's old. That is, if you're trying to do it naturally. You can't do it that way. It doesn't work. The stuff we can see shouldn't be arranged the way it is. There shouldn't be galaxies out there at all, and shouldn't be stars out there in the galaxy. On top of that, if there are galaxies, they shouldn't be grouped. Stars are a problem. Groups of stars and galaxies are a problem. Now we got groups of galaxies. Just multiply the multiplication. galaxy clusters, the Hercules cluster of galaxies organized. It just multiplies beyond our imagination, the problem of trying to explain it naturally. We hear a lot about this solar system, and especially in the earth science textbooks, they say this all condensed from the nebular cloud. This here's the dust, and it spun around, and it is condensed into these planets with the sun in the middle. Not a very good fairy tale, which is about the best you can say about it. All kinds of problems. First, the sun has 99% of the mass, where the planets have 99% of the angular momentum. Now, if you're a physicist, you understand this is all condensing out of the same cloud, and here's the mass, and it's not moving very fast, but these things out here that have virtually none of the mass are just going up a storm relative to the sun. How did they get going so fast when the great mass is just plodding along? You know, that's not going to work. This has a slow spin. The planets have rapid orbital motion, which is not going to condense naturally out of a cloud. Sir Jeffreys of Cambridge says, I think all the suggested accounts of the origin of the solar system are subject to serious objections. The conclusion in the present state of the subject would be the system cannot exist. That is, naturally, if it's been there for a long time. And again, there's another refrain. More recently, 2007, just a couple of months ago, this fairly up to date, and they're talking about planet formation theories. And what they find when they put this on the computers is, okay, you get some boulders and some rocks here, they're supposed to come together to form a planet, and what happens? The boulder goes right to the sun. This planet formation theory has been a stumbling block for 30 years, which of course you've read about in your earth science textbook. No. The reason is that boulders tend to fall into the star in a celestial blink of an eye. There are enough uncertainties that planet formation is not going to be an open and shut case anytime soon. He said, we don't know how that collapse into a planet actually occurs. In spite of the fact your earth science textbook tells you just that happened, it just condensed out of the cloud. No, we don't know, and when we try to explain it, we fall flat on our face. Same thing is true with the moon, and we could spend a whole evening talking about the problems there, but here from nature, many models have been proposed for the formation of the moon. No one has succeeded in showing how it had formed successfully. Jack Lissiter with the NASA space program says, all in all, developing a theory of lunar origins that makes sense of the data proved very difficult. The best explanation was observational error. The moon did not exist. One of the ways to test a model is to see how the predictions take place. If stars didn't exist, that's what we'd expect. There shouldn't be galaxies. They shouldn't be grouped together. The solar system shouldn't exist. The best explanation is the moon didn't exist. But you read the textbook and it's like, we can explain it all. What can they explain? It all flies in the face of their naturalistic explanation. The basic laws of nature say it will not work. And so when we back off and look at the two models, and we see the obvious prediction of degeneration and decay by the creationist as defined by what we read in Genesis, degeneration, decay, imposed as a consequence of sin. All right, let's test that against what we see and see what fits. That's what we see. The evolution model says things are going to go uphill, and they have great faith, and everything from microchips to brains, it's all going uphill. But what do we see in the world we live in? Your own experience with your houses and your cars and the bodies. And is it going uphill or downhill? Well, we know that. When we look at the life of the past, we see dramatically things were bigger and now then they have gone downhill, which they don't like to admit, but it's just as obvious as it can be. When we look at the universe around us, when we look at the sky, we see everything from stars to the face of the planets to the comets to the planetary nebula, the just stars blowing themselves out of existence, galaxies, everything is going downhill. That's not what they predict. Now, just be honest. Which model explains what we see best? Now, I don't think it's a hard question if a person's honest. Let's think before we conclude about some implications of this and allow Isaac Asimov to acknowledge what he sees as a real problem. He says, as far as we know, all changes are in the direction of increasing entropy, increasing disorder, or increasing running down, randomness. Yet the universe was once in a position from which it could run down. Now, the natural processes, everything we see, say it goes downhill. How did it get up? It had to be up from which it could run down, but natural processes say you don't go that way, it goes this way. How did it get into that position? You see, the second law of thermodynamics says there had to have been something besides the natural processes we see to explain what we're looking at. And there's no way around that. H.J. Lipscomb is an atheist, writing in Physics Bulletin, but faces the issue squarely. He says, I think, however, we should go further than this and admit the only accepted explanation is creation. I know this is anathema to physicists, as it is to me, but we must not reject a theory we do not like if the experimental evidence supports it. And it's not, again, the Sunday school lesson that's telling, this is the law, the laws of science that govern this universe, and it says you can't do it naturally. It doesn't work. You can't explain anything that you see in the universe around us, and it certainly doesn't fit the picture that we see on this earth. The experimental evidence says, obviously, the creation model works better. I want to conclude with a statement by two very brave men. They are creationists, but they're the authors of the textbook that's used in virtually every undergraduate thermodynamics in the country. Every university in the state of Texas that I know, I've been able to check, and that's most of them, use their textbook. Now, people will say, maybe you're a hard rock geologist, archaeologist, what do you know about thermodynamics? Well, I may not know a whole lot, but these fellows do. They wrote the book. We see the second law of thermodynamics as a description of the prior and continuing work of a creator. Naturally, you cannot get it here where it can then be seen to be going down as we do now. You can't. And so that second law that says everything goes down says natural law is not going to account for this. You've got to have something beyond the natural in order to see what we're seeing and see things go downhill. It also holds the answer to our future destiny and that of the universe. It's going down to destruction. And that's clearly implied from the laws of nature, from these fellows who really know what they're talking about. I think that is a powerful bit of evidence and should be obvious to people who are willing to look.